In this screencast, we're going to show how we can calculate the change in Gibbs free energy for a reaction at elevated temperatures. We're using information we have at 298 from tables. And in particular, we're interested in the case where the heat of reaction is a function of temperature and heat capacities are a function of temperature. And it's the same procedure where we're talking about delta G for formation or delta G of reaction. So the starting point is the Van 't Hoff equation. Let me pause and write that down. So the Van 't Hoff equation relates delta G, and the subscript T means at a certain temperature. Superscript 0 means we're looking at delta G at standard conditions. This partial respect to T is related to heat reaction, which is also a function of temperature. R, in this case, is the gas constant. So if we integrate this, let me again write that down. So we integrate between the temperature of interest T and our reference temperature. And our reference temperature that we're going to use is 298 Kelvin because that's a temperature we have data in tables. And so the integral delta H, remember, is a function of temperature, and so let's look at how we do that calculation. So delta H, the heat reaction, standard conditions at some temperature, is the heat reaction at our reference temperature, again standard conditions, plus the integral from the reference temperature to temperature of interest. In this term delta Cp, I'll explain this in a second. So this is Cp for each component in the reaction. This is the stoichiometric coefficient, which is positive if it's a product and negative if it's a reactant. So the heat capacity for each component is a function of temperature, and the way we're going to express it is in terms of constants A, Bi, Ci, T squared, and then Di, T cubed. And of course these are available in tables. And then this summation, we're going to have a number of terms, and let's look at an example to make it a little clearer. So our delta Cp is going to have terms for delta A, delta B, etc. And so delta A then would be 2 times the heat capacity of the product, and then minus signs for reactants, heat capacity of nitrogen, and then 3, stoichiometric coefficient, heat capacity of hydrogen. So knowing the heat capacity form, we can now write the heat of reaction in terms of the delta A's, delta B. So I substitute in, and now I can do this integration. So here we have the integration, and what I want to do is rearrange the terms so that it'll make it a little easier to do the calculation. So I've grouped these such that all the terms are independent of temperature, which is all of these terms. They're just dependent on our reference temperature, which we fix at 298. And we're going to use notation that's common in textbooks. And we'll call this capital J just to make it a little easier to work through the calculations. So I'll write this down once more in terms of J. So I've written down the equation again that I presented earlier that tells how Gibbs free energy changes as a function of delta H. And then delta H is in this boxed in equation. So now what we want to do is make this substitution for delta H of T, and let me do that, and then we'll look at the integration. So I've brought the gas constant outside the integral, divided through by T squared. Now I can integrate this. Remember, the first term on the right side is just delta G at our reference temperature that we get from a table. So I've written down the integrals, and I've indicated the limits that we're going to apply. So now I'm going to apply those limits, and I'll rearrange the equation a little bit so again we can group terms that are independent of temperature. So just like we did before, we're going to take all the terms that are independent of temperature and we're going to group them together, and we're going to call this I. Again, this is notation that's fairly common in number textbooks. And so then we'll end up with the equation that we can use in the spreadsheet, and I'll just write that down. So this equation is a real objective here. We now can calculate delta G as a function of temperature by calculating I, which requires us, of course, to calculate J. They're both a function, of course, of the reaction, but they're not a function of temperature. And then we have the temperature-dependent term that we can then see how, as we change temperature, delta G changes, and of course then we can use delta G for a reaction to get the equilibrium constant for a reaction. So this delta G could be delta G of formation reaction or just a overall general reaction. So we posted a spreadsheet on LearnChemE that applies this equation to make it a little clearer, and then also listed here the equations in type form in case that is easier to visualize.